after this session. And this is important for the, presenters for the first day. Please don't forget it. Okay.
So this session is going to be chaired by Mustafa Akdogan from the Bolo University and me, Alexander Dobrovolsky from the University of Vienna. And it's my great pleasure to invite here the speaker of this half-plenary session, Professor Fomin, who is a research professor at the Solid State and Material Science Institute, Leibniz Institute in Dresden, Germany, and is a honorary member of the Academy of Science of Republic of Moldova. Professor Fomin is theorist known for his contributions to various branches of physics, including functional nanostructures for magnetism, optics, semiconductors physics, and superconductivity in 3D nanoarchitectures belongs to the topics Professor Fomin has been contributing for a good decade. So, Vladimir, stage is yours, and it's my pleasure to introduce your talk now. So.
Thank you, Chair. Good afternoon, ladies and gentlemen. First of all, I would like to thank the organizers of this nice conference, and personally, Professor Ali Gencer, for inviting me. This work refers to the realm of 3D superconductor nanoarchitectures, and these are two places where I have been working. It's Dresden and Chisinau, it's capital of the Republic of Moldova. Four. Here is the outline, very brief. I will give, in fact, a definition of superconductor nanoarchitectures, and then more specifically will introduce a few of them. In particular, open superconductor nanotubes, recently unveiled topological transitions in curved superconductor nanomembranes with some interesting peculiarities depending on how the transport current is switched on and off. Then superconductor helical coils, and most recent, still ongoing research on topological transitions in modulated transport currents in such nano architectures. At the end, when I have time, I will speak about perspectives. Advanced superconductor nanoarchitectures feature very attractive physical properties like very high magnetic field inhomogeneity, non-trivial topology of superconducting screening currents in them, and complex dynamics of different topological defects. This was a part of my recent book on self-rolled micro and nano architectures, published last year. A kind of overview of this advanced superconductor nanoarchitectures was provided this year in our perspective paper together with Professor Dobrovolsky here. And there are very prominent technological advancements which have made possible in the last 2 decades, in fact, to produce such novel structures. And one of them is self-rolling, which has been mastered by our Institute in Dresden and also in many other laboratories in the world. And another one is focused electron or ion beam deposition. And there can be also natural self-organization of such nanoarchitectures. We can recall carbon nanotubes. They are nanoarchitectures which are naturally organized, but now there are very, very many representatives of this class. What is self-rolling? This is here a very short reminder to those of you who are not aware of this approach. Let us take a bilayer of two materials with different crystal lattices and put it on a third layer, which is white. This is a sacrificial layer. It's all on a substrate. If you etch off this sacrificial layer from a side of this structure, then these two films, which can be a few monolayer thick, are under significant strain because of mismatch of their crystal lattices. And this strain should be somehow realized, and it is realized in deformations. There can be different deformations, but under certain conditions, this deformation is rolling. And it can be 180 degrees rolled part. It can be 260 degrees, a full tube, or it can be many, many rolls which give already a new nanoarchitecture which can be called radial superlattice. What is important here for our presentation? That this is certainly a nanotube, but it is not a complete closed nanotube. It's an open nanotube because this edge, which I show now, is free. And there could be special efforts in order to glue it in a nanotube. But we will speak about such self-rolled nanotubes. Another very nice approach, which was already mentioned today in our session, it's self-organization due to chemical reaction of precursor molecules under focused electron or ion beam and moving this focus in space. We can produce very different geometries. Here it is an example of a helix. If the focus ascribes a helical path in space, then these molecules which are under the effect of this focused ion beam,
recording stopped.
They are forming a nanohelix, for example, but this path can be extremely different, thus producing a great variety of structures. And I already mentioned this rare metal dichalcogenide nanotubes. In the same natural way, one can even form a Möbius ring of niobium triselenide, but this is a little bit outside of my topic. I want simply tell you that there are different well-established experimental approaches who give us nanoarchitectures. Please. Nanoarchitectures in 3D are in fact two-dimensional manifolds like films or stripes, which nevertheless are shaped in a form in 3D. So they are not 3D in fact, but they are developed in 3D. Oh, can you go further? No? Let's wait a little bit. Okay, I still have here a first slide. If we consider such a superconductor nanotube, look, here is a slit, and put it in a magnetic field orthogonal to the axis. The main difference between a planar film and a rolled up nanotube is in the following. In a planar stripe, the screening current, Meissner current, in fact they are small, they cannot expel magnetic field, but Meissner-like currents, they flow along the perimeter. It's a loop which is singly connected, that is, it belongs to the whole structure. But if you rolled up, you have rolled up a nano tube and put it, as I said, in a magnetic field which is orthogonal to the axis. There are two loops of superconducting screening currents developing in the upper, conventionally, and in the lower part of this tube. And they are independent from each other. And they are topologically disconnected. And already at this very early stage, I have shown you even how they are fabricated. We can deduce that they will reveal some topologically non-trivial features of superconductivity, like development of two different loops of superconducting screening currents. And it's clear that this will lead to some at least interesting, unexpected properties of superconductivity. If this is a superconductor under conditions when there are vortices, then in a planar film, the vortices arrange themselves, okay, in a line, if it is narrow, in two chains, if it is wider, or in a kind of abricos of lattice, if it's wide enough. But this is a unique array. And if you have two, oh, very good. If you have two halves of a tube, you will have two sets of vortices, one in the upper part and another, one in the lower part. And their dynamics was, in fact, the object of our, oh, please, next one. Initial stage of investigation. So we had this, yes, and wow. Okay, thank you. Thank you. I went already a little bit ahead of this slide, but so these are examples of representative three-dimensional nanoarchitectures which were fabricated really. So what I am telling you about, it's a theoretical work, but it has been motivated by these wonderful advancements in fabrication and characterization technologies. This is an example of self-rolled nanotube. At that time, it was 2 micrometers radius, but now it's below 1 micrometer in diameter. These are self-rolled helices, which are produced in the same way, but if you use a gamma-like stripe to roll up. And this is one and second examples of direct written nanoarchitectures. Next, please. Yeah. I was telling you that there should develop 2 different loops, 2 sets of screening currents. And one more interesting thing, that it is an open nanotube, and it's possible and technologically feasible to attach contacts to 2 banks of this slit. And it's easier to do than to make this tube full. If you send then a current, here it is a DC current, from one bank over this azimuthal path to another bank, then there will develop Magnus force in this system, which will influence the eventual vortices, but here the current is from right to left, and here it is from left to right, because of the fact that this is self-rolled nanoarchitecture. Therefore, the Magnus force will act on vortices in this direction, in the upper part, and in the opposite direction, in the lower part. One more important remark before we go further. These tubes are really very narrow. The thickness of typical niobium rolled up tube in the previous slide is 50 nanometers. And the radius can be 1 micrometer or 2 micrometers. Therefore, they are really very, very thin. Therefore, the vortices we will speak about, they are not like Abrikosov vortices from a textbook, because Abrikosov vortices are long. There are lines with a core. And in this case, I would call them as slices of Abrikosov vortices, which have very, very small height. But nevertheless, they have all the topological properties of rotating currents around the core. Next, please. This is a very brief presentation of our theoretical approach. We are using time-dependent Ginzburg-Landau equation supplied with Poisson equation for the scalar potential, with Maxwell equation for the vector potential, if we like to consider renormalization of the magnetic field. And then within a link variables approach, in order to take into account gauge invariance, we project this set of equations onto a lattice. It's shown here. In fact, 2 lattices, one lattice for order parameter, another lattice for velocities or vector potential. And in this sense, we would like to emphasize this paper by Valéry Vinocourt, who established this approach for planar structures. But we are applying it for curved structures. Please, next. This is how the Ginzburg-Landau equation looks like in terms of the link variables, maybe from this slide, without going into details which are available for theorists if you are interested. We have here a typical sizes of mesh, 250 by 250 in earlier calculations. Now these numbers are increased up to 1,000, and typical number of iterations to solve this set of equations with appropriate boundary conditions is 100,000 to 1 million. It depends on the system and mainly on its size. So, next slide, please. Yeah. And this is an example of what we obtained. In the right-hand side, we have two vortices in a planar field, and in the left-hand side, we have two vortices in the tube. This is the surface of the tube. Can you push on now? Yes, yes. This is very important. In a planar structure, the vortices move as governed by Magnus force. But I told you that there are two different, please put it once again if possible. Yeah. Vortices move in one direction, in the upper part, in another direction in the lower part. So dynamics of vortices is already highly non-trivial. And this is a correlated motion. When one vortex is nucleated on one edge in the upper half of the tube, another vortex is nucleated in the lower half of the tube in the opposite edge. And then they move like shown here. We investigate certainly their dynamics, and they feel each other because they belong to the same state of a superconductor. They are not independent. But when they are in the central part of this path, I will show it in the next slide, they are slowed down a little bit, and then they are again enhanced in their velocity. And in order to anticipate possible questions which are very, very typical, the dynamics which will be discussed here, it's typical of thin tubes or helices. If the tube becomes thicker, then suddenly the vortices become more developed, and they start feeling each other inductively. And when this, would say, opening of a tube is very small, we have already a trend of formation of a Abrikosov vortex through the tube, and certainly then there is no such dynamics. There is only deformation of Abrikosov vortices. But again, this is a case of narrow tubes. Please, next one. Next. Okay. Depending on the magnetic field, we can have regimes with one or less than one vortex, with a chain of vortices, with two chains of vortices. And here are two critical parameters. In terms of time, it's the time of flight from nucleation to denucleation, and delta τ2 is period of nucleation of a vortex at a certain edge. And depending on the ratio between these two times. We can have sparse vortex regime like here, or dense vortex regime like here. Please, next one. The relation between these two times is a strong function of radius. And here we plot these times as a function of the applied magnetic field. And you can see that when changing the radius, we change this both times very strongly. They are all shifted to the lower magnetic fields when radius is increased. So that the difference between typical magnetic fields of transition between two regimes or simply starting of the motion of vortices, it can be changed in the range of a numerical factor of 7 or even better. So it's not a small effect, it's very, very, very pronounced effect. This, what I was presenting you, refers to the case when the transport current is relatively weak. Already in this regime, we can state that the control of the properties of superconductor in the form of vortices is very significant. But if we increase the transport current towards critical values, we arrive at very interesting and unexpected topological transition that in spite of some arrays of vortices, we will see phase slips, like shown here in the bottom part. But this is an announcement. Let us go to the next slide. Yeah. So these are typical pairs of distributions of autoparameter in a planar film above and in an open tube below. No time for this. Next one. Yes. Here, very interesting observation that if we take a planar film, niobium, this is all about niobium. These are typical values of magnetic field, critical when the process starts or transition from one regime to another regime. And let's roll it up. We do nothing. It's physically the same plate of the same material, but once not rolled up and another rolled up. We see here a shift of this typical characteristic magnetic field by a factor of 3. Isn't it remarkable? It shows that the geometry of a nanotube influences physical properties. It's another tool for control over the physical properties of superconductors. Next one, please. Yeah. Here, how to explain a transition from single chain to two chains. Please put on both, yes. Single chain we discussed, but double chain you will see now. It's magnetic field which is not yet sufficient to embed two chains. And what do the vortices do? They show a bifurcation. They start as a single chain, and then they move into different paths. And these two paths have different typical time as shown here below. So bifurcation allows to accommodate such a number of vortices which cannot be divided by number of vortices in one chain. So this transition is easily realized by bifurcation. Please, next slide. Yeah. This is our system with a little bit more detail. I told you already a single loop when there was no picture, and in a tube there are two disconnected loops in a nanotube. Next one, please. And this is very, very unusual development. Let us try to follow this same transition, but at enhanced currents, when transport current is already of the order of critical, still subcritical, but strong. It occurs that the system does not show this transition via bifurcation in this case, but the transition occurs via formation of a phase slip in a part of a tube which is opposite to the slit. First we obtain all this, and we try to go with more and more to resolution, and we were not practically able to see anything. But then we plotted a phase portrait of this same stage. This is the phase of the order parameter, and it was clear what happens. Here, just on a line opposite to the slit, in this case, pairs of vortices and anti-vortices are spontaneously generated. We can check it by simply calculating the change of phase when we encircle these topological defects in one direction. And then, under the influence of the Magnus force, they start moving. If a vortex from a pair meets an anti-vortex from another pair, they annihilate. If an anti-vortex from the first pair meets a vortex from the third pair, they annihilate. But they move with such strong speed that even their lifetime is 3 orders of magnitude smaller than for vortices in chains. They can produce very prominent induced voltage. And what is induced voltage? It's a measure of deviation from superconductivity. It's a measure of induced resistance due to the motion of vortex-anti-vortex pairs. And on the characteristic induced voltage as a function of the magnetic field, this regime is represented by a peak. We have a peak of magnetic field induced voltage versus magnetic field characteristic. And what is interesting in this stage from topological point of view, we know already that in a tube there are 2 loops of screening currents. But in this regime, we see that former 2 loops are pushed towards the banks of
Recording
the
in progress.
slit, and there develop 2 more loops of screening currents, shown here by green. We have already 4. It's more complicated topology. And just between these loops, we have a locus of formation of vortices and anti-vortices. Please, next one. We have already discussed this. Please, next one. This is another material. For tin, it's equally good. Next one. Yeah, we have seen it already. Next one. Yeah. Okay. In recent work, very recent work, we considered this transition in more detail, and if there are states with vortex change and slips, phase slips, then depending on the direction of changes of current or magnetic field, we can see hysteresis. Please, next one. Next one, still next one. So these are two cases depending on the ramp time. When this ramp time is large enough, only vortices appear, but if the ramp time is small, so we can in fact visualize the metastable state with phase slips very confidently. Next one. Next one. Yeah. Okay. Next one. Good. This is a hysteresis. Next one. Yeah. The last few minutes I will devote to other nano architectures, and one of them is helical coil, which was produced by different methods. Next one. There is incommensurability of the vortices in different half windings of such a tube, which certainly are influential for transport. Next one. And this is an experiment which was already discussed by Professor Cordoba in our session, when the experimentally observed steps in resistance as a function of the current in such a nanohelix was explained by the occurrence of a few or more phase slips in half windings of this helical structure. Next one. Next one. Yeah, this is how does it develop on the number of half windings. Next one. Yeah, this also influence of an electric field. Next one. And very recent work was devoted to response of nanoarchitectures on modulated transport current. Next one, which shows a very rich set of transitions between vortices, phase slips, and combined structures, which certainly are reflected in the voltage as a function of time. Next one. Very interestingly, in this case, we can see also phase slip joints which are not along the axis, which are orthogonal. So in dynamics, new phase slips develop. Next one. This is another example of the same, depending on the modulation depths. So we can control which kind of defects will appear. Next one. And click 2 times more. Okay. Depending, and once again. Yeah. Depending on the frequency of modulation, for example, we can have either a state which is superconducting with relatively low voltage response due to surface stages without superconductivity, via stages which have both part of the sample which is superconducting and a part which is normal. Therefore, we have a kind of beatings in the voltage as a function of time, which are reflected in the fast Fourier transform to the state when almost the whole sample is already normal, and certainly it gives only frequency of the modulated current. Next one. This is simple, similar dependence on the magnitude of the current. Please, next one. Next one, yes. And this is, in fact, a final slide, which will be partly discussed today in our session at 15:20. But from these traditional structures, which are we are moving now to novel nano structures which can be fabricated, like this hat. And in this hat, we have already three-dimensional phase slips, which certainly open a new avenue for controlling the superconducting properties of such nanostructures. This opens perspectives both for fundamental knowledge and for applications, like filters, switches, sensors, bolometers, detectors of terahertz radiation, fluxonic devices for information processing, and squids and other Josephson devices in nanoscale and curved. And next one. So these are my thanks to collaborators. I am afraid I will not have enough time to name all of them, but please read, and to funding agencies, and I thank you for your attention.
Thank you very much for your nice presentation. Because of the delays of time, probably we have time just for a couple of questions, please. If any, just raise your hand. Yes, please.
Thank you for a nice talk. So I have a question about quantum phase slips. So vortex is a topological defect in superconducting order parameter, and there is a structure of eigenenergies levels in the core of vortex, and there are quasi-particles occupancy. So do we have similar features in case of phase slips, and to what extent movement of phase slips is deterministic process?
Certainly, there is an analogy between the structure and energy structure of vortices and phase slips and in their dynamics. But there are significant differences between these types of topological defects. Vortices are well defined, and though dynamical due to the superconducting currents in a vortex, they are defined entities, and they can be treated even within molecular dynamics as quasi-particles, if you know the interaction potential, which is already well established. But phase slips is a more complicated situation. It's a phase defect which is temporarily developing. It develops in time. Sometimes the definition names them as phase slip events. And they are represented, for example, by occurrence of some line or some region, one-dimensional or two-dimensional, even three-dimensional, with suppressed superconductivity. But there is a very rich dynamics of vortices and anti-vortices in our case and in many other cases within this entity. So therefore, if we're speaking about phase slip, we cannot simply attach some energy spectrum to it, because it's something more complicated. It embeds maybe 10 pairs of vortices and anti-vortices with their own energy spectra, which are moving, which are occurring and annihilating. And in this sense, a description of a phase slip cannot be reduced to the same instrumentarium as the description of a vortex. It's simply more complicated. One should take into account more conceptual ingredients for a phase slip.
Yes, please.
Thank you.
Phase slips in field theory are not topological defects, are instantons. So they're tunneling events. So they're topological defects in Euclidean spacetime. That's the difference. So they are events, not topological defects.
Okay. Do we have further questions from the audience? Seems not to be the case. So let's thank the speaker again. And on
Thank you.
This and related topics we will continue in hall 3 in 5 minutes after a short break. So Vladimir, good. It's my pleasure.
There is an announcement again. Please don't forget putting your
Thank you.
words to the voting box for the first day presenters, please.